Good morning, ladies and gentlemen. My name is Yagawa. I'm pleased to open the plenary lectures session part 2 today morning. We have two distinguished speakers today morning. First speaker is Professor Terada. And I'd like to introduce him later on. And the second paper will be chaired by Professor Shabel Farhad. He will come soon, I guess. Okay, so first I'd like to introduce Professor Terada. Kenjiro Terada is a professor at Tohoku University. After finishing his Bachelor of Science from Nagoya University in Japan, he completed his master degree and doctor degrees in applied mechanics in University of Michigan. Dr. Terada has published more than 170 referred papers in the field of computational mechanics, with the quality of his distribution being recognized with many awards. For example, he awarded the IACM Fellow Award this year, last Monday, you remember. The main thrust of Terada's research is development of mathematical modeling and computational techniques for heterogeneous materials by means of computational homogenization method. In this context, he proposed a generalized finite element method called the finite cover method to realize mesh-free like analysis of composite materials and structures. He has been a board member of JSS and serving as vice president of JSS currently. He is recently selected as a member of the executive council of IACM. Professor Terada. His paper is entitled here, Multi-Scale Computational Diversified from Material to Disaster Sciences. Professor Terada.
Thank you very much, Professor Yagawa, for your kind introduction. I also would like to thank the organizers of this special event to inviting me to here. It's a great honor to be. It's a great honor to be here. Good morning, everyone. I'm Kenjiro Terada from Tohoku University, Japan. Today I'm going to talk about the multi-scale computation diversified from material to disaster science. Okay, let's start with this slide here. Here, this is my hometown Sendai. This Sendai is often subject to the earthquake here. Then this is the bridge, the typical infrastructure here. Then on this bridge, there are many cars here. Then this car is composed of several metals. They are planning the multi-scale computation. We can replace some of them by this kind of magnesium as a structure member. Then look at this coastal area. We also can apply multi-scale computation to assess the stability of this kind of rock mass. Okay, on this rock mass, we may have this kind of nuclear reactor building. And in this building, we also have some material that suffers from fracture due to aging and chemical reaction. So this kind of phenomena, we also can apply the multi-scale computation to evaluate this kind of macroscopic behavior. Then, at the same time, we have the tsunami on the coast, the damage by tsunami is also can be predicted by Mudscale computation. So with this overview, we have 3 topics today in this presentation. One of them is the method of two-scale analysis method for nonlinear solid and plates, with emphasis on the decoupled two-scale analysis for nonlinear solid. The other 2 topics are the applications of the idea of numerical material testing for material science and also disaster science. In this context, we extensively utilize the nonlinear homogenization method. So I'd like to give you this brief historical development of nonlinear homogenization method in this context. So let us begin with this first topic. As you know, the theory of the homogenization method was originally developed in 1970s and early 80s, mainly in France, Italy, and former Soviet Union and the United States. These are the famous mathematicians in this field. As you may know, Babushka was the godfather of the homogenization method. Then in the late 80s and early 90s, the method of homogenization method is introduced into applied mathematics and engineering fields with the help of finite element method. It is emphasized that thanks to the localization capability of the method, the theory enables us to perform two-way coupling analysis between the micro and macro scale that shows the superiority over the micromechanics. After the late 90s, many researchers interested in nonlinear homogenization problems, and also the linkage with computational micromechanics was extensively discussed. During this period, we have this meeting. According to my survey, it is in this meeting that the term Mudscale first used in the field of computational mechanics. So after that, the popularity of Mudscale becomes clear. It is maybe wrong, but according to my survey. Then, for nonlinear homogenization programs, there are several branches. The work done by Suke was highly important in this field, especially for inelastic problems. This work was followed many researchers. However, the most of the development are concerned mainly with the macroscopic material behavior without solving the corresponding macroscopic boundary value problem. This is probably due to the fact that the mathematical theory of the homogenization method does not provide any functional form of nonlinear constitutive equations. So many researchers have tried to develop micro-macro coupled FE analysis. As you may know, this is also known as FE square, nested FEM, and multi-level finite element method. This is a list of such early development in this context. Then this slide shows you the typical example of the coupled method. Here is my macrostructure. We solve this macrostructure, equilibrium problem of this macrostructure without any macroscopic constitutive equation. Instead, in order to obtain the macroscopic stress in this field from the macroscopic strain, we solve the microscopic equilibrium problems at every Gauss point and in every loading step simultaneously. Okay, as you can imagine, and also some of them you already experienced, this method is very time-consuming, even if we apply parallel computations. Also, this method is almost impossible to be implemented into the existing C software. Okay. More importantly, this method, inherits the limitation of the mathematical homogenization method. That is, we cannot deal with the strong nonlinearity, including microscale background, like that. So we note that for weak nonlinear problems, it's very easy to find macroscopic constitutive laws. So my assertion is that the homogenization-based two-scale analysis method are readily applicable for the situation in which the macroscopic constitutive equation can be found or can be constructed with reference to the constitutive laws assumed at the microscale. This way, I gave up this coupled method 10 years ago. although I was the one who originated of the decoupled method. But now I recommend the decoupled two-state analysis method that is studied and validated in these references. Let me show you a very simple numerical example using this kind of unit cell, which is composed of the carbon fiber and polycarbonate matrix. Before conducting the numerical material test based on the homogenization method, we prepare the data for the microstructure, that is the geometry of unit cell, a material model assumed for the constituent, and also the material parameters for the assumed model. We assume the carbon fiber is linearly elastic, but polycarbonate should exhibit some sort of nonlinearity. This slide shows the stress-strain curve of the polycarbonate matrix, which shows weak nonlinearity. As you can see, rate-dependent plastic deformation can be found. At the same time, we can see the stiffness reduction in unloading process. Okay, so in order to represent this kind of material behavior, we introduce this constitutive equation, that is elastoplastic creep damage model that exhibit weak nonlinearity. This equation is very standard, so we don't need to explain the detail of the equations. But to look at these parameters, these are the parameters, unknown parameters for the material. So we have to identify those material parameters before conducting numerical material tests. So after identifying the material parameters of this material polycarbonate with reference to the experimental data, we can conduct numerical material tests on this unit cell. That is, we can apply these 6 patterns of macroscopic deformation into the unit cell here in order to obtain the macroscopic mechanical behavior. This shows the numerical material test result. This shows the actual response in the X and Y direction, with the Z direction. These are the shear responses of the unit cell. As you can see, this macroscopic response well reflects the unit cell geometry here. Then let us move on to the next step. And we have to identify, or we have to assume the macroscopic constitutive equation to represent such kind of macroscopic response. For that purpose, here I put the ansatz that the macroscopic constitutive law inherits the characteristics of microscopic one. That is validated in this article. Then I employ the anisotropic version of the microscopic constitutive equations employed for the unit cell. That is the anisotropic elastoplastic creep damage model. These equations are almost the same as the equation assumed in the microscale, except for the anisotropy that can be represented by the Hills parameters in creep and plastic strain. So by using the different Hill parameters, plastic and creep flow rules, we can characterize the anisotropic inelastic deformation in this material. So these are the material parameters to be identified on this model. This model has 39 parameters. So we have to apply some sort of optimization method to identify these parameters. In this study, I applied the particle sum optimization, which is one of the population-based descent method. Then we applied this method to identify these 39 parameters. We could obtain this kind of identified curves in comparison with the numerical material results. Okay, as you can see, the identification is quite successful. So we can move on to the macro scale analysis. By using the assumed macroscopic constitutive equation and also the material parameter identified, we can conduct the macroscopic stress analysis. Here, this is my macroscopic structure, which is the typical specimen of the fiber reinforced composite. To demonstrate anisotropy, the fibers are oriented this direction. These are the analysis conditions, but the details of the condition are not important in this context of the demonstration. Here shows the macroscopic analysis result, that is the overall response. And this loading process and unloading process, we could have this kind of macroscopic deformation together with the stress distribution, which shows this kind of anisotropy, which reflects the fiber orientation here. So we can move on to the next step, that is localization analysis. That is, we can pick up the macroscopic sampling point here, then extract the macroscopic strain history, then we impose that strain history onto the microstructure to have these kind of microscopic mechanical behavior of unit cell during this macroscopic deformation. Okay. So it can be expected that this coupled analysis, the decoupled analysis, has the same accuracy with the coupled analysis. We expect that. In addition, this decoupled analysis is very cheap compared with the coupled analysis, as you can imagine. Okay. So let us move on to the next topic. So because of the feature of the decoupled method, implementation of this method into existing finite element software is very easy. So let me show you the commercialization here. This shows the GUI menu of ANSYS, which enable us to perform the Mudscale analysis by using this GUI. This product is called Mudscale Chain, developed and sold by Cybernet System Japan. These are the collaborators of this development. Here shows some function installed in this software. Here you can see the homogenization part, which involves the numerical material testing for weak nonlinear materials here. Also, this function has the macro scale analysis, and also we can conduct the localization analysis within this software. So as you can imagine, since the micro and the macroscopic analysis are standard finite element analysis, so we can utilize all the material models inside of this software as well as the existing pre- and post-processing functions in this software. This is very easy to analyze. So let me show you a very simple numerical example using this software that is decoupled two-scale analysis of three-point bending test. As you can see, this is the localization analysis result during this macroscopic deformation. As you can see, the fibers are damaged in the tensile region of this macrostructure, and also the matrix is damaged in the compressive region of the macrostructure. Okay, this table summarizes the feature of the Mudscale SIM. This product provides linear homogenization capability for various physical problems. You can see here. And also look at this table. This product provides decoupled two-scale analysis of capability for various weak nonlinear problems. Okay. So let us move on to the next topic. That is decoupled two-scale analysis for nonlinear plates. Because the time is limited, I just put the result. This is the example of composite plate with in-plane periodicity. Here's my example. In this case, this is a two-scale decoupled plate analysis for floor slab with asphalt mixture. Here is the macrostructure. This is the microstructure. Then this microstructure is just a unit cell model with in-plane periodicity. Is modeled by 3D solid elements. On the other hand, this macroscopic plate model is generated by laminated plate elements. Here we assume this kind of material behavior for the asphalt concrete. We assume the viscoelastic plastic type, and also concrete is linearly elastic. Okay, then we apply the method of numerical plate testing in order to have the macroscopic plate stiffness. That is, we apply the generalized strain on the unit cell to have the generalized stress like this. Then this is the numerical test result. As you can see, this is the in-plane deformation. This is the bending and twisting deformation. Here is also the out-of-plane deformation. Okay. Then we could have this kind of relationship between the macroscopic generalized stress and generalized strain. Then we identified some material parameters for each layer. Then we could make the macroscopic analysis that set up this in this figure. This is the bridge, the floor slab of bridge. This is modeled by plate laminated shell element here. then we can have this kind of micro and macro response of the floor slab. This is the example of decoupled analysis of plate, composite plate here. So let us move on to the next topic, that is the numerical material testing in material science. We have two topics today. One of them is the characterization of the macroscopic ductility and the toughness of magnesium yttrium alloy. This is the joint research to utilize magnesium alloy as a structural materials in lightweight cars. Okay. Here, this is a typical stress strain curve, pure magnesium, and also the curve for the magnesium alloy. This pure magnesium shows poor ductility and toughness because this material suffers from the cracks in the microstructure like this. On the other hand, this magnesium alloy shows good ductility and toughness. It is clear the effect of yttrium is the enhancement of ductility and toughness. Then look at this microstructure. This is the polycrystalline aggregate of the magnesium alloy. Then we apply compressive loading in this microstructure. We have this kind of deformation twinning here with crystallographic slip. After the final stage of deformation, we could have this kind of dynamic recrystallization, which involves the grain refinement. These two kinds of deformation mechanism, that is deformation twinning and also dynamic recrystallization, probably make the material more ductile and tough. Okay, so I'd like to simulate this kind of complex microscale deformation in order to characterize the corresponding macroscopic material behavior. So in order to do that, I will introduce the deformation gradient for the twinning deformation here. This is the twinning deformation gradient between the elastic and plastic component of the deformation gradient. All the other equations are the same as the classical theory of crystal plasticity, so I will skip the most of the equations associated with the crystallographic slip. But here is the standard expression of the resolved shear stress. Here is the Schmidt tensor here. And this is the famous typical expression for flow rule using Schmidt factor. And also this is the hardening law and the slip rate here. But we have to be careful about the characteristics of slip system and critical resolved shear stress of this material. That is, these are the slip surfaces of the hexagonal close-packed crystal of magnesium. The very important feature of this material is the critical resolved shear stress of the basal slip here is extremely low compared with the other slip system like here. So this feature makes the material less ductile and thus makes the plastic forming very difficult. So in order to be more ductile, the magnesium should have other deformation mechanisms. One of them must be deformation twinning, like this. Okay, can you see? Oops. Here. So I have already introduced the twinning deformation gradient here. So we assume the twinning deformation gradient of this form. Here is the twin configuration tensor that can be determined geometrically. And some of them are depicted in this figure here. And also this variable, this is the internal variable that represents the volume fraction of the piece variant of the twin deformation gradient here. So we introduce this free energy that contains the internal variable here. And we take the standard process within the framework of thermodynamics to derive this kind of evolution equation that is the flow rule of the internal variable. This is the corresponding driving force of deformation twinning. Together with the deformation twinning and the crystallographic slips, we also have to consider the grain refinement, which caused by the dynamic recrystallization. So, in order to represent this kind of grain refinement, we employ the multi-phase field method with this free energy. And then we take the standard process to derive the evolution equation for order parameters. This is the evolution equation, which involves some standard terms here for the multi-phase field method. But here you can see the special term composed of gradient of pyramidal slip that we assumed as a driving force of grain refinement. Okay. Here shows a numerical example under compression. This is the typical distribution of the deformation twinning. As you can see, 101/2 twinning is more likely to be active compared with this deformation twinning. And also, during this deformation, we could have this kind of microscopic stress distribution together with the plastic deformation like this. As you can see, in the region of the twinning deformation, we could have this kind of small value of plastic strain. At the same time, we could also have the distribution of the gradient of pyramidal slip we employed as a driving force of the dynamic recrystallization. This is just the distribution density. This is the distribution of the gradient of pyramidal slip. Okay, so using this information, we could perform the dynamic recrystallization by using the multi-phase field method, like this. Okay, we performed coupling simulation of crystal plasticity finite element method and also multi-phase field method in order to evaluate the nucleation and the grain growth, like this. At the same time, we could have this type of macroscopic stress strain curve. Okay. So now on, we have to clarify the mechanism for the macroscopic ductility and toughness by investigating this kind of microscale deformation and also the macroscopic response here. But unfortunately, we haven't done yet. This is ongoing research, so I don't have any research result further. So let us move on to the next topic. The next topic will be the assessment of the macroscopic strength and durability of the polycrystalline metals, which involves microscale cohesive cracking due to the hydrogen embrittlement. As you know, the hydrogen is a very important element in the energy engineering here, like this. Then when the hydrogen diffuses along the grain boundary in this kind of polycrystalline aggregate, then the material suffer from the strength degradation, which may be caused by this kind of electrochemical reaction. This kind of strength degradation is called hydrogen embrittlement, okay? Which eventually causes the segregation of the grain boundaries. As a result, the macroscale strength also decreased with cracking. But unfortunately, the interaction between the micro and the macroscopic fracture process have not been fully understood yet. So I'd like to characterize the macroscopic strength and the durability by analyzing the microscale cracking in a polycrystalline aggregate, which is subjected to the hydrogen-induced degradation. For that purpose, I assumed the absorption hypothesis as a mechanism of the hydrogen embrittlement. This slide shows the modeling of the hydrogen embrittlement with the help of the cohesive crack model. Following the Griffith theory, I introduced the cohesive potential of this form. With this cohesive potential, we could derive cohesive traction like this as a thermodynamics force. Here we have D is the damage parameter, whose evolution equation is given here, which represents the nucleation and propagation of the cracks. Okay. At the same time, this potential is multiplied by the fracture energy, which is the function of the hydrogen concentrations. This is the equation relationship for the fracture energy for a new crack surface, which represents reduction of the cohesive force as the hydrogen concentration is increased, as shown in this figure. This figure shows the relationship between the crack opening and also the cohesive force here. Okay, this is the numerical specimen for my microscale cohesive cracking. This is a kind of polycrystalline aggregate. In order to represent the deformations, plastic deformation of this material, we employ the classical theory of crystal plasticity as well. With this evolution law of slip rate and also the slip resistance like this. These are the material parameters I assumed for the numerical material testing here. Here shows the diffusion process of the hydrogen in numerical material test. Here, this is the time variation of the hydrogen concentration. We used this diffusion coefficient that is borrowed from this article. With this time variation of the hydrogen concentration, we can determine the material parameters of the proposed cohesive crack model. Then we can conduct a numerical material test, that is the microscale crack propagation, like this. This upper here shows the crack propagation without hydrogen diffusion. On the other hand, here, the result with hydrogen diffusion. As you can see, the crack speed is much higher than this result because this material is subject to the hydrogen diffusion that is suffer from the hydrogen embrittlement in the microscale. This result is also reflected in the macroscopic cohesive response. Here shows the relationship between the macroscopic cracking opening here and also the macroscopic traction force here. As you can see, the macroscopic strength here is decreased as the exposure time to the hydrogen is increased, which promotes the hydrogen embrittlement. Okay. So next topic, we move on to the numerical material test for disaster science. Okay, and this is the material to disaster. Okay, the scale is totally different. We have 3 topics today. One of them is the two-scale stability analysis for seabed, or that rock mass with coastal levee. Okay, here shows the Japanese islands. Here we have the Shizuoka prefecture. We may have this kind of nuclear power plant subject to the earthquake and tsunami here. But today, I'm not interested in this facility here, but I'm interested in this seabed close to this plant on which the coastal levee and intake towers are laid on. Here, the rock mass composed of green tuff. Here shows the green tuff region around this, in these islands. This coast is covered by this kind of alternate layered rock mass, okay, which has this kind of microstructure, which is composed of the mudstone and sandstone. This is microstructure, although this has this dimension here. Okay, so the mission is to assess the stability of the seabed, that is rock mass, that supports the coastal levee or intake tower subjected to tsunami. For that purpose, we have to conduct a numerical material test to characterize the macroscopic strength by considering the anisotropy in deformability and strength, and also we'd like to consider dependency on the consolidation stress. At the same time, we consider the elastoplastic behavior in compression and also the quasi-brittle failure in tension. Okay, so for that purpose, we introduced first the material models for mudstone and sandstone. For the compressive deformation, we employed the classical theory of plasticity, that is J2 flow theory. This equation is very standard, so we don't need to explain the detail. But here, for tensile deformation, we employ the continuum damage theory to represent the quasi-brittle fracture. Here is the Fuchs law, which involved the damage parameter here. This damage variable, the function of fracture energy and the tensile strength. And here we have the maximum value of equivalent strength ever experienced. Here is the definition of the equivalent strength given by this guy. And also we provide the failure criterion like this. Then, as I mentioned, we have to consider the anisotropy in deformability and strength, and also the dependency on the consolidation stress. That is, we have to consider the material property that depends on the consolidation stress, which is a function of the depth of the seabed here. This is intake tower, this is the seabed. Okay. So this slide shows the typical stress strain curve of the rock mudstone and sandstone, which exhibits the dependency on the consolidation stress. As you can see, the flow stress of this curve is increased, the consolidation stress is increased, as you can see. Then, with this material information, we can perform the numerical material testing for this kind of microstructure composed of mudstone and sandstone. So that I'd like to impose these kind of macroscopic deformation into this unit cell to have this kind of numerical material test result. That is the macroscopic material response in compression. Okay, these are the actual response and the shear response. As you can see, the result is that the deformability and yield strength exhibit a strong anisotropy. Okay. So in order to represent such kind of anisotropic response, we employ the Hills model for anisotropic plasticity as well. And this is the standard orthotropic elastic tensor for the generalized Hooke's law. And this is the standard expression for the yield function by using Hill's equivalent stress. So we don't need to explain the detail, but here we have the material parameter to be identified. So again, we apply the particle swarm optimization to identify the material parameters. Here is the identified curves in comparison with the numerical material test result. The two curves are almost identical, so you can see detail, but the identification was quite successful, as you can see. Then we have to also evaluate the dependency of the material parameters on the consolidation pressure. So as you can see here, these are the functional representation of the dependencies. Then now, this is the macroscopic material response in tension as a result of the numerical material testing on the unit cell that exhibit quasi brittle failure in tension. Okay, as you can see, depending on the macroscopic loading patterns, we have an isotropic characteristic, the macroscopic tensile strength, like this. So we can put these all material response in the macrostructure, macroscale material response to this kind of envelope of macroscopic strength. Here shows the tensile region of the material response, and this is the compressed region of this macroscopic material response. Then we can utilize this kind of envelope for the macroscopic strength assessment. Now, let's conduct the macroscopic analysis of the seabed of alternate layered rock mass composed of this unit cell. The external loading on this seabed comes from the coastal levee here, which is attacked by the fluid force generated by tsunami. For tsunami simulation, we set up this domain. Here is the water wall, have the initial water level here. And also this is the flow direction, and this is the coastal levee. And we put here dummy blocks here. Then this is the analysis result. This shows the wave hit the coastal levee so that the fluid force transmitted to the seabed. Okay. Then the stress acts on the seabed like this and like this. Okay, this is the macroscopic deformation with stress. Then we can evaluate, or we can assess the macroscopic stability of the seabed by using the envelope of this macroscopic strength. Here is the envelope. Here we pick up the 4 points of the macroscopic material point. Then we can recognize this point B is a possible failure position in tension. Okay. At the same time, we can conduct localization analysis based on the homogenization theory, so we can extract the deformation history of this of these material points to the unit cell to have the microscopic mechanical behavior selected at the of interest here. These are the microscopic mechanical behavior obtained by the localization analysis. Here, look at this. This is the point of possible failure in tension in macroscopic viewpoint. Here is the microscopic response that suffer from the damage of the sandstone here. So we can assess this kind of strength, stability of the seabed from the macro and the microscopic viewpoint by applying the decoupled two-scale analysis method as well. Okay, so next topic will be the numerical material test for fluids in multi-scale tsunami simulation. That is, I will present the multi-scale modeling for tide barrier globe. Here, the tide barrier globe attacked by tsunami. We first separate the spatial scale. This is the scale of overall arrangement of globe. This globe is composed of several trees like this. And this tree is composed of branches like this in the local region. Then we define the representative volume element for these branches. Okay. Then we perform the numerical material test on this region to have the loss characteristic of the flow for phase one. We conduct numerical material test in phase one to have the macroscopic loss characteristics for phase two. Okay. Then we applied numerical material test on this phase two to have the macroscopic loss characteristic for phase three. Okay. Well, for that purpose, we have to put the governing equation for the phases 1 and 2 and 3. This is very typical standard Navier-Stokes equation, except for this term. This term is the porous media parameter to represent the effect of the pressure loss by branches in phase 1, trees in phase 2, and globe in phase 3. This term can be evaluated by numerical material test each scale. Okay, so in order to solve this equation, we employed this stabilized finite element method with stabilized parameters like given by test here. And that is the SUPG method and PSPG method along with the shock capturing method are employed. Also, we use the BOS method, BOF method for free surface representation like this. Here, this is my representative volume element here. Here is the test surfaces to measure the pressure loss. Here is the flow direction for phase 1. So by changing the combination of entry speed and water volume versus total volume in our representative volume element, we conduct numerical material tests on this for flow with obstacle in order to have the loss characteristics of phase 2. Here shows the numerical material test of phase 1 in order to have loss characteristics for phase 2. Here shows the time variation of pressure loss with different entry speeds and water contents. This curve shows the response when the water speed is 2.5 meter per sec and the water contents 0.5. This is the typical flow state. Then, taking the spatial average over the RVE and also taking the temporal average for the period of steady state flow, then we could have this kind of response surface of the pressure loss for the phase 2. By using this information for the phase 2 loss characteristic, then we can conduct numerical material test on this phase 2. Here is again, we have the representative volume element for phase 2. This is the test surface to measure the pressure loss here. Then this is the flow direction. Then we can compute the macroscopic pressure loss for phase 3 here. This is the coastal levee, the globe. Then for various sets of entry speeds and ratio of water volume of the RV volume here. This is a typical result of flow state in phase 2, that is the numerical test result on the RVE, in order to have the macroscopic loss characteristics for phase 3. Okay. Here shows the losses. Then we can perform the phase 3 dynamic simulation in order to investigate the effect of the tide variable law like this. As you can see, this is the without the variable law. This is the with variable law. You can see the effect of variable law can be properly captured by this 3-scale simulation. Now let us move on to the final example. This is the flow with Labo. Because the time limited, I will quickly talk. This can be recognized as the heterogeneous fluid with obstacle, that is tsunami with Labo on March 11, 2011. So we'd like to have the equivalent homogeneous fluid to estimate the fluid force. For that purpose, we set up a numerical viscometer to evaluate the dynamic viscosity and density for the overall flow. Here is my viscometer, numerical viscometer that's modeling. Then here includes the several rigid bodies, square logs, bars, and spheres, rhombus. Then we applied the finite cover method for the microscale fluid structure interaction analysis to evaluate the viscosity and density at the macro scale. This finite cover method is originally developed for structure analysis, but we applied this method to the structure interaction. Here shows quickly what is a finite cover method. Define the geometry of the structure, then generate the meshes for structure, then superimpose the meshes. This is independently generated. Then define a regression function inside, outside the structure. Then I extract the physical cover located in the interface between those structures. Then finally, we can define the location of the interface by the regression function and regenerate the meshes for fluid. Here shows the numerical result of the viscometer with Labo. Then we can evaluate the macroscopic viscosity and density by using this test result. Then we can perform macroscopic analysis, that is the tsunami simulation with viscosity and density evaluated by numerical material test. Here is the homogeneous water, which is equivalent to the heterogeneous water with Labo. Here shows the result. Tsunami hits the structure to destroy. This way, this reflects the effect of the Labo in terms of macroscopic viscosity and density. Okay, this is all my presentation. Let me conclude my presentation with this slide. Okay, so let's enjoy the diversified multi-scale computation. Thank you for your attention.
Thank you, Professor Terada, for your excellent lecture. I'm sorry to say that we don't have time to discuss discussion. So if you have any discussion, you can ask him during the coffee time. Thank you very much. So next paper will be chaired by Professor